In this section, we're going to talk about uniform circular motion, and you have to imagine a particle moving around the circumference of a circle at a uniform rate. That is moving at a constant rate around this circle. Now, theta is a central angle in this circle. The radius is r, and this arc length is s. That would be the amount of distance the point would travel on the circle in a time t. Now, the linear velocity, if the point goes from here to here and covers this distance s in a time t, then the linear velocity of that particle is v equal s divided by t, just distance divided by time, and that will be our linear velocity. The angular velocity is the amount of angle rotation that this goes through in an amount of time t, and that's defined as omega, which is, by definition, theta, the amount of angle that you go through in time t. So it's this angle theta right here, measured in radians, divided by t. The relationship between linear velocity and angular velocity is the linear velocity is the radius times the angular velocity. If you want to see the derivation of this, you have to look in the book. So imagine that this point P travels a distance of, let's say, 5 feet in 2 seconds. Then its linear velocity is going to be 5 feet divided by 2 seconds, or 5/2 feet per second. If the amount of angle that it goes through, let's say it goes through pi radians in 3 seconds, then the angular velocity is going to be pi over 3 radians per second. So let's go to the board now and work some problems that involve uniform circular motion. Suppose that the distance s that's traveled along the circumference of the circle is 12 centimeters, and it takes 4 seconds to do that. Let's find v. Well, v is equal to s divided by t. That's going to be 12 centimeters divided by 4 seconds, and that will come out to be 3 centimeters per second. Now, what that looks like is, suppose we have a circle, and a point travels from here, let's say, to here, and that's a distance of 12 centimeters, and the total amount of time that it takes to do that is 4 seconds. Well, then, the linear velocity of that point along the circle is going to be 3 centimeters per second, because it goes 12 centimeters in 4 seconds, so its linear velocity is 3 centimeters per second. So linear velocity is pretty easy to find. It doesn't depend on the radius of the circle. All we need is the distance traveled and the amount of time t. We divide distance by time, and we end up with linear velocity. Here's our next problem. Suppose, on the other hand, that the velocity is 20 feet per second and the time t is 4 seconds. You want to find the distance that's traveled along the circumference of a circle using this uniform circular motion. Well, I'm going to use the same formula. V is equal to s divided by t, and I'll simply substitute in v is equal to 20, s is what we're looking for, and t is equal to 4. So I substitute those numbers in, I multiply both sides by 4, and I end up with s is equal to 80 feet. Now let's see if that makes sense real quickly. Suppose I have a circle. Okay, I have a point that's moving along the circumference of the circle at a uniform rate, and it covers 20 feet every second. How far is it going to go in 4 seconds? The distance that it's going to travel in 4 seconds will be 4 times 20, or 80 feet. So I can still use the same formula right here, and it does make sense intuitively when I think about traveling around a circle at a constant rate of 20 feet every second. If I travel for 4 seconds, I'm going to cover 80 feet on the circle. Now, we don't know how big or small the circle is, but we do know that we're covering 20 feet around the circumference of the circle every second. So I just substitute into the formula anyways, and I get s is equal to 80 feet. Let's look at another problem. Suppose that the angular velocity, omega, is 4 radians per second, the radius of the circle is 2 inches, and the amount of time that the particle has traveled is 5 seconds. Let's find the distance that it's traveled. Well, I'm going to start with my formula for v, and v is equal to s divided by t. Now let's see, I'm looking for s, and I'm given t, so I've got part of this filled in, but I need v. Well, v is also equal to, besides s over t, the other formula is r times omega. So s over t must be equal to r times omega, because v is equal to s over t, and v is equal to r times omega. So let's substitute in using this equation right here and see what we get. So s divided by t, so I have s divided by 5, is equal to r, which is 2, times omega, which is 4 radians per second. So I get s is equal to 2 times 4 times 5. When I multiply both sides of this by 5, 2 times 4 is 8, times 5 is 40. And that's 40. Let's see, s is my arc length. I have radians per second and inches, so this is going to be 40 inches. So if I have uniform circular motion in which a point is traveling around the circumference of a circle with angular velocity 4 radians every second, the radius of the circle is 2 inches, and I let this thing go for 5 seconds, the total distance that I'm going to cover is 40 inches around the circumference of the circle. Let's look at our next problem. 10 RPMs is what omega? So by this I mean 10 revolutions per minute. What I have here, RPM stands for revolutions per minute, is what as an angular velocity, because a lot of problems in real life you see are given in terms of RPMs or revolutions per minute. So let's see how we can convert RPMs into angular velocity, and then use that. We could solve a lot of other problems. Here we go. So I have 10, and I'm going to write this as revolutions per minute. Now I'm going to multiply this by a conversion factor that's going to have me end up with radians per minute. So what I have is this: 2 pi radians are in 1 revolution. So 1 complete revolution around the circle is 2 pi radians. You can see that my revolutions will divide out right here, and I'll have 10 times 2 pi, which is 20 pi radians per minute. So 20 pi radians per minute is the same as 10 revolutions per minute, and that will always be the case. So I can change from RPMs to angular velocity anytime I want by multiplying by 2 pi radians per revolution. The revolutions will divide out here, and I'll be left with radians per minute, which is the units for angular velocity. So that's a quick look at linear velocity, angular velocity when we have uniform circular motion, and the relationship between those two velocities.